Weird. Hi, Cece. How are you?
Hi, Nicholas. How are you?
I'm good.
Great.
I see Andrew's here. Hello, Andrew. How's it going?
Good. How are you doing?
No complaints. I see Ven is here. Ven, how is everything in your corner of the world?
Things are going really well. Thank you, Nicholas.
I'm glad to hear that. So the question that I asked to start off today's class was, what do you do to relax and take care of yourself when you're not learning data science? Of course, Lambda's super intense. We're always focusing, go, go, go. But a really important part of working hard is giving yourself time to relax and decompress. So for me, I like to journal. I'm a big journaler. I like doing a little meditating, though probably I should do it more than I do. And I love playing with my niece and nephew. In fact, I was over there last night playing hide and seek. Logan's saying Logan's a big gamer. Is that right, Logan? I see you have that gamer chair, so I get it. I get it. Andrew's also a gamer, spending time with the girlfriend. Definitely a great way to decompress. How about other folks? What do you do to chillax, as the youth are saying today? Kaji says she likes to sleep. Oh, I wish I was a better sleeper. That's wonderful. Walk, nap, read to my kids. Nothing better than reading to your kids. That's the best. I love reading stories. Devin, gaming for sure. Totally. My wife is a big gamer. She likes VR. So I'm always like coming into the living room and she's jumping around or something. And you just gotta politely walk around. So what are some of these games? What are the games that folks like to not watch, play? What are sort of the big gamer games that folks like to do? I don't think I've gamed since like Sega Genesis. Or the Wii. I'm a pretty good Wii bowler back in the day. League of Legends, absolutely. Definitely. I've been learning a lot about, students do a lot of data science projects with that. Loop Hero, interesting. Loop Hero. Is that like a time loop, Devin?
It's I'll unmute myself and talk about it. It's like a roguelike kind of. You have like a randomly generated map and you go around it like every certain amount of time, and you make it harder as you go to try and like get loot to beat the boss. Came out like 2 weeks ago, maybe early this month. Pretty
nice.
New. Yeah.
Okay, sounds cool. That reminds me of a Nintendo game I used to play, Excite Bike, where you just ride around the circle over and over again. Or what was that show I was just watching? Snowpiercer, where they go around the world every year? I'm not sure. Awesome. Well, there you go. Recommend 2 thumbs up from Devin for Loop Hero. Is that right? Okay, very cool. 7 Days to Die, Cyberpunk 2077, Microsoft Flight Simulator. I know that game. I used to play that when I was a kid. Factorio, Oxygen Not Included, Elite Dangerous. Wow, a lot of good recommendations from Logan. Got to check out some of these out. A lot of data in the gaming industry. People are trying to figure out what users are kind of gravitating to in a game, which features work, which features don't. Doing that sort of statistical testing you learned in Unit 1 is going to be super important, called A/B testing, but also just being able to show executives, designers, other folks, a sort of analytics of the game, how many users are on the platform, the demographic nature, the sort of demographic profile of your user, super, super important. So, data is a big part of the gaming industry. Zunaira likes to spend time with her nephew. I love that. How old is your nephew, Zunaira? Just turned 2. Oh my goodness, 2, adorable. Wonderful, wonderful. Family always comes first. That's great. Okay, so let's dive into today's class. Let's get started. We're here in the last guided project of the sprint. So we've got some final ground to cover before we move on to the sprint challenge tomorrow. So we're going to be focusing today on classification metrics. And if you remember one thing from today's guided project, it's that there is more to classification than just accuracy. Let's think about this for a second. Why am I saying this? Well, let's say that I am building some sort of predictor, and maybe I work in a hospital and I'm trying to predict based on MRIs whether a patient tests positive for a very rare brain condition. All right, let's say this brain condition makes them possibly one of the best gamers in the world. It kind of automatically makes them for-loop heroes. And so we need to get them on the national for-loop hero team. And that's why we're doing these brain scans. But let's say that only 1% of the population has this brain condition. All right, so 99% of the people I scan will not have this. And let's say that I build a model, I build my cool neural network, and I go to my boss and I say, hey, I built a model, and guess what? It has 99% accuracy. That's right. My model is almost 100% accurate, 99% accuracy. So the question is, should my boss be impressed that my model has 99% accuracy in identifying, or rather 99% accuracy in distinguishing between people who have this brain condition and who don't? Devin says no. What do other people think? Andrew also says no. I'm hearing a lot of nopes and nos, but tell me a little bit why. Give me some more answers. These one-word answers are tough to follow. Why is it not impressive that my model has 99% accuracy? Then is all about the bonus. You got to get the bonus first, right? And Andrew is raising a really good point, and Devin is also, if 99% of your population doesn't have this condition, your model, your baseline is 99%. Your model could just basically say, hey, this person doesn't have it, this person doesn't have it, this person doesn't have it. It'll always say no, negative, 0, and it'll still be 99% accurate. So really, you don't need a neural network at all. You just need a person saying no, 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 right? And so that's why sometimes accuracy can be very misleading, especially when you have these data sets that were what we call imbalanced, where your one class, your majority class is really big, and your minority class is really small. And Logan is thinking about like, hey, what about false positives and false negatives? And that's going to be a little bit of a preview of what we're going to be talking about today. But the one thing I really want you guys to remember is that there is much more to classification than accuracy. And you got to think about what your model is doing and where you're going to use it, especially when you're looking at these metrics. So here is our roadmap. You can see that we have just been crushing it this week, if I do say so myself. We've done all of our wrangling. Hold on, let me get my stamp. We've done our wrangling. We've done our building. We're like pros with the decision trees and the random forest regressors. We now know how to do feature importance, and we know how to do hyperparameter tuning. So we've really got everything cooking. We're cooking with gasoline here. And just the last thing that we need to be doing today is we need to be looking at what are these classification metrics, these new classification metrics. So that's the final piece of the puzzle. Okay, so how are we going to tick off that last box? Well, we're going to be focusing again just on the check metrics part of this workflow. And specifically, our goal is, I want to tweak this whole model and the whole Tanzanian water pump data set kind of problem. And then I want to think about how we can optimize the way that we repair water pumps. So let's think about putting this model into action, maybe helping an organization or maybe even helping the Tanzanian government efficiently repair water pumps. Now, in order to meet that objective, there are a few things that we need to hit along the way. First, we need to get and interpret what's called a confusion matrix for classification. We need to talk about new classification metrics. We need to evaluate our model using new metrics like precision score and recall score. And then we need to understand the relationship between precision score, recall score, and thresholds, something that we talked a little bit with our logistic regression problem. So that's what we're going to be focusing on today. Now, my game plan is I said I was going to tweak this Tanzanian water pump problem. Right now we have a multi-class classification problem. And the first thing that I want us to do is I want us to turn it into a binary classification problem. And I'm doing that not because you need to do it, but rather it's a little bit easier to discuss precision and recall in the context of a binary classification problem. Although everything we're doing today applies to to multi-class as well. From there, we're going to create our confusion matrix. We're going to look at how to calculate precision and recall score. And we're going to use precision and recall score to optimize the way that we do water pump repair. So that is our plan. However, before we do anything, I feel like it would be a good idea to maybe just do a little bit of a warm up and activate some of the important ideas and vocabulary that we're going to be using today. So let me just start with a little warm up survey here. And what I want everyone to do, I can see that there are 13 of us. So let's see if we can get, I'm feeling optimistic. Let's see if we can get 9 answers, 9 or 10. So put in your answers and let's see how we do. All right, already a third of the way there. Oh, over half, 2/3 of the way there. So 3 more. This is quick. This is quick. We're already up to 10. I wonder if we can get 11. Oh my goodness. Excellent. It's a coup. It's a lambda coup. Wonderful work, guys. Okay, so let's take a look at y'all's answers and then we will look a little bit about what's important here. So the first question I asked you guys is, which of the following metrics is used to evaluate a regression model? So a model that is predicting some sort of continuous value, you know, like between 0 and 1,000,000, like for our New York City rent problem. And the options were accuracy score, precision score, recall score, and mean absolute error. Now, what did you guys say? Well, most of you said mean absolute error, and you're absolutely right. So mean absolute error, and there's a little bit of a clue here, which is, you know, when we're doing a regression problem, and I'm going to draw this in red here. There we go. When you do a regression problem, you have these points. Now I'm doing this in 2 dimensions, okay, but this can be multiple dimensions. But you have these points and your model is trying to find the best fit, the best kind of line of fit among these points. And it's never going to be perfect, so there's always going to be some error. It's kind of shooting for, you know, it's trying to get 0, but it's never going to be perfect, so there's always going to be some sort of error. And that error, you want that error to be 0, but it can go way, 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 way up, depending on the nature of your problem. Now, the clue then is that when you're doing classification, there's really no close in classification. You can get close in regression. Oh, it was 100, but you got 101. There's really none of that in classification. It's either yes or no, right? You either got it right or you didn't. And for that reason, these error, if you see a metric that ends in error, it's really not going to apply to classification. So that's where these scores come in: accuracy score, precision score, recall score. All of these scores go between 0 and 1, and 0 is what you do not want, and 1 is what you do want. Of course, the one exception there is R² score, which is for regression, but let's not worry about that. Okay, beautiful. I'm super psyched about this one. Let's move on to the next one here. All right, next, in the attached code, which of the following is a hyperparameter? Interesting, interesting, interesting. So what did you all say? Let's see here. And you all said, 82% of you said it was K, and you're absolutely right. You're absolutely right. So a hyperparameter is going to be something that you, the data scientist, set in your model before you train it, okay? So it's basically a way of, it's a knob you're turning to affect the way that your model is built. So K is 20, means limit yourself to 20 features when you're doing your select K best. If we sent it to 18, it would just select 18 features, whereas Ridge is the predictor. So there's nothing, it's like you're either using the predictor or not. There's no knob here. If we were looking at the alpha for Ridge, how tightly do you want to rein in your crazy coefficients? That's another issue. But in this case, it is K equals 20. You guys are absolutely right. I'm feeling really good. Let's move on to the next one here. All right. The last question, and perhaps the most exciting and important, is have you selected a data set for your Build Week project? Now, the correct answer here is yes. And I can see that we are a little bit at half and half. I'm not loving this, guys. All right. But keep in mind, everyone, that today is the day to submit your project. Oh, excuse me, not submit your project, submit your Build Week data set. So let me just open up Student View here. There we go. If you go to modules and you look at Build Week project submission, this is where you are going to submit the data set that you're going to be using for Build Week. And I want to really underline here or emphasize that you will be using this project, you will be using this data set to complete your module projects next week. So if you don't have a data set this week, you won't be able to do your work next week. And that means that you'll be starting Build Week a week behind everyone else, right? So you need to make sure, this is a requirement, that you have that Build Week data set ready to go on today by 4. And that way CC and I will have a chance to look at it, give you the green light or the yellow light or the red light or whatever light we see as necessary. And then we can make sure you're in a place to succeed both in Sprint 3 and in Build Week. So do not go another day without a data set. All right, that's it for my ominous warnings. Thank you guys for the warm up here. Let's stop this and let's go to the water pump challenge. Wow, we have a lot of administrative stuff today. Zunaira has taken the lead with just 2 entries. Great work, Zunaira. The Big Hustle Award goes to Logan and Angelo for their 5 submissions. And really, everyone is doing great. Everyone's up above 80%. You guys are just points away from the state of the art. Keep in mind that this is only 50% of the data. So these metrics are not complete. I wouldn't trust them. Things could change between now and noon on Friday. So if you haven't submitted a data set, excuse me, hold on. If you haven't submitted a submission, now is the time to do it. And if you're curious about how to do that, watch the video from yesterday's class, and that's where we go over how to put a submission in. But great work, guys. I love, love, love seeing the improvement on these models over the course of the week. Okay, with all of that in mind, let's just, I'm going to take a little stretch here. Loosen up the scalenes, got to get the delts in order. You really got to warm up before you do data science. You don't want to pull a muscle. Take a deep breath, a deep cleansing breath, in through the nose, out through the mouth. And let's move into today's project. So a couple things that you guys know well by now. I'm going to start with our little preamble here, install category encoders, and then I'm going to install or import all of the libraries, and pretty much all of these should seem familiar to you now. The only one that you haven't seen before, we're still going to be in the metrics module, but we're going to be importing the plot confusion matrix function and the classification report function. So a couple new types of metrics. So I'll import those into a memory. And the next thing that I'll do is I will wrangle my data. Okay. So here's where our first challenge lies. If I look at, for example, DF, what is it? Pump status, something like that. Status group. And we look at value counts. We have 3 different categories here. And here's what I want to do. I want us to go from a multi-class classification problem to a binary classification problem. Specifically, I want us to create a column that's going to be called something like needs repair. So I'll call it needs repair. And we can almost think of this as like needs repair, question mark. When you're putting together a binary column, it's a good idea to think about, like, can you phrase it in terms of a yes or no question? And so we would have the functional group be one possibility, and those observations would be coded as a 0 for no, they don't need repair, false. And then the other 2 groups, the non-functional or the functional needs repair, I want to have those be our ones in this case. So in this case, it would be needs repair. Yes, true, positive. Those would be a 1. So this is what I'm shooting for here, going from multi-class to classification, going from multi-class to binary. Functional, 0, we're going to call that our negative class because it's 0, negative, false. And then the 1, we'll call that our positive class. So yes, true, it does need repair. So how can I take this? How can I take what we have now and convert it into binary? What are some ideas that you guys have? We don't need code here. Let's just throw out ideas. Hector, what do you think? Tiana, CT, what do you guys think? Angelo, give me some ideas here. I'm loving these ideas already. So Hector has the idea of a one-hot encoder. That could totally work. We have the idea of an apply function. That could also work. Yep. Let's see what else we have. We could filter the current column and make a new column, Snaira. That's a great idea. Curtis has the idea of a function as well. So kind of in the Venn camp. let's look at a couple of these different solutions, and then let's choose one, because you always need to choose one in the end. Let me clear my drawings here. Okay, so let's look at a couple options. The first is, let me scroll up here. Let's start with Hector's option. Okay, good. We already have our one-hot encoder. So one thing I could do is let's see how I would do this. I would do one-hot encoder. Let's do use cat names equals true. And then I could do fit and transform. Note here that if you want to do it in just one line of code, you don't need to do fit and then separately transform. You can do fit transform as one. And then what I can do is I can do df, and I'll have to pass in, I think I have to pass in a data frame, although I'm not sure. Let's just do status group and see what happens. Let's see what comes out. Let's just see what comes out of this first. Let's see if this runs. Okay, it does run, and we get a data frame. So what I can then do is I can look at the head of this data frame. There we go. So now I have this one-hot encoder, and I have status. I know we have two groups, right? So I know that I want everything here. I want all of these ones to be 1. And then everything here in this column, I would actually want this to be the opposite of what it is. So I would actually want ones that are functional, I would want them to be a 0. And then the ones that are not, the ones that are zeros, I would want them to be 1s. So I would have to kind of invert this column somehow. So that's one option. I think we're moving in the right direction here, right? We're moving to the direction of 1s and 0s. I think, though, let's try another idea here and just see if we can get exactly what we want without having to do any kind of additional transformations. So I'll just put this here, and I'll say, let's see here, Hector's idea, one-hot encoding. Excellent work. Thank you, Hector, for that idea. The next one is we could use some sort of filter, right? Some sort of filter and make a new column. Well, let's think how I would want to do this. How would I write a filter to just give me one, like I just want one of these groups. I don't really care if it's like the positive class or the negative class, but I want to get one of these groups. So how can I write some sort of filter that's going to distinguish between functional on the one hand, and then the non-functional and the functional needs repair classes on the other hand? So what would this kind of mask or true-false statement look like? What do y'all think? So Devin's idea is if it equals functional, then what we want is a 0, and otherwise we want a 1. Okay, I like it. And Logan has the idea of doing an iLock here. Let's see what this is. Well, let's kind of combine. Let's combine the idea that, let's combine Zunaira, Curtis, Ven, Devin, and Logan all together in one fell swoop here. So let's see here. I'm going to scroll down, and I could then do, for example, so let's say we have DF status group equals functional. And let's just look at the first, say, 10 rows of that. Okay, beautiful. So here I have this true, true, false, false kind of thing. So that's possible. The other thing that I could do, check this out. What if I said instead of equals, what if I used instead this little exclamation point and said if it doesn't equal functional? Whoops, sorry about that. Now I have what I want. I have false or 0 for my functional group and true or 1 for my other group. So if I did this as type int, let's see here, and then I looked at the head. Now I have what I need, which is basically the opposite of this column here. I have 0, 0, 0, 1s, etc. So it looks like this is a good way to do it. This gives me exactly what I need. So what I could do is I could say something like, let's see here, DF needs repair equals this column, which we just created here. So if I run this, and then I look at my data frame again, so let's look at df.head, and I scroll all the way to the right, I can see here, this is going to be my new target. Beautiful. And so I actually don't need to create like a special function or then apply that function. In this case, we can just do it with this little evaluation statement. So we can kind of combine what you all have said and just do it with this line of code. Excellent work. I love this. Now, credit where credit is due. Let's put in everyone's name here. So this would be Zunaira. Let's see here, CT, Ven, Devin, and Logan. And by the way, there's another way to do this. Now that I'm just thinking about Hector's idea, what I could do, for example, is I could do, let's say that I have this data frame, and let me save it. Let me save it as, I'll just call this target, okay? Actually, I'll call it binary target. There we go. And if we look at binary target.head, this is the same thing we were looking at before. There we go, beautiful. So what I could do here is, I know that if something has a 1 in the status group non-functional or in the status group functional needs repair, if it has a 1 in either of those columns, then I know that I can see it as a 1. So one thing I could do is, for example, I could do something like, let's think about this. What if I just limited myself to these 2 columns? So I'll paste these in here. I'll have to put in these. There we go. Have to put in all of the proper stuff. There we go. Now let's look at head. Now, what I need to do for Hector's idea is that I need to sum across the columns. I need to sum across the columns. How could I do that? How can I sum across the columns? How do we sum across rows? So Curtis is saying I can add them, right? I could do binary target status group non-functional plus status group functional needs repair. That's one way. If I'm, for example, looking at just one series, how can I take a series and sum it? Like, for example, if I was looking at just one group here, so I had, let's say I had binary target, and let's say that I wanted to get the number of, let's say I wanted to just get the sum of this entire column. How do you sum a column in pandas? One thing you can do is you can just do sum, right? So if I did sum here, I can see that in my binary target in the status group non-functional, I can see here that there is a 22,823. But the other thing is sum actually has an access argument in it. So if I do the default here, so let's say I do sum dot sum, and the default here is access is 0. So if I did it like this, I would basically have value counts. It would tell me that non-functional, there were, if I'm summing downwards, so think 0, 0 gravity, you're going down. I get 22,000 here and 4,000 here, but that's what I don't want. I don't want to sum up, down. I want to sum across. And so what I can do is I can actually do a 1 here. And now I have a sum across the rows. And then, for example, I could do equals 0. Because if there's a 0, no, wait, hold on, let me get this right. Wait, I need to focus. I need to focus. It would be if it's more than 0. Because if it's more than 0, it means one of those two columns had a 1 in it. So if I did it this way, let's see here. There we go. So for example, this column is true. Okay. And then I could do, let's break this up a little bit here. I got to use more, let's see here. Sum axis 0. There we go. And then I would do, oof, this is a tough one. And I would do as type int. There we go. Beautiful. So this here is going to be the same as this column which we just created. So 0, 0, 0, 1, and here it is 0, 0, 0, 1. So two ways to do the same thing. Thank you, Hector. That was a good idea. All right, beautiful. So we have two ways of doing this. Any questions about these? All right, let's take this one-liner and let's just create a new feature here. So we'll say create new target. There we go, create new target. Beautiful. Excellent. So I'll run this. I've added it to a wrangle function, and I get an error here, which is status group. Hold on one second, what's going on here? Let's see here. I get an error. It says status group is not in the columns. What am I missing here? Why do you guys think I'm getting this error? It says status group isn't there. let's see where I'm getting this error. I'm going to expand this, and I just want to kind of roll up through the stack here. And I can see that the place where I'm getting this error here is in X test, when I try to do X test. So the line of code that's throwing the error is this line of code right here. And then Hector is saying, didn't we drop status group in a previous class? Status group is our target, so we didn't drop it. But it does seem like, yeah, remember that our test data doesn't have that target. That's why it's test data. So that's why we're getting that error. So how can I rewrite my code? How can I move, what can I do to this line of code so that it works for my training data, but it doesn't do anything for my test data? And then saying you can use an if statement, definitely. And Devin saying, wait, we already have an if statement. And you're absolutely right, Devin. What I can do is actually just move it up here to where we were doing this before, where we had slightly different behavior based on whether we had a target vector or not. So if I rerun this, here we go. Beautiful. Now this is looking good. Okay. Static. And then what I'll do is I'll just comment everything else out here so that we can, if we need to rerun this. Whoops, sorry. Excellent ideas, guys. I love it. You know, like this is why pair coding is so important. You know, if you're working with your mentor or you're working in your track group, you can always see kind of more things going on, and it's always super, super helpful. Beautiful. Okay, so let me just rerun all of this to make sure we're running with a fresh data frame. There we go. And then the next thing that I'll do is I'll move to my splits here. Actually, let me stop. Let me pause. Any questions about this wrangle function and the changes that we've made to it today?
Yeah, I have a really stupid question, but why are we doing this? Why classify them into functional versus needs repair?
Okay, two things. One, there are no stupid questions. All questions are valid. And if you had that question, I'm guessing that somebody else also had that question. Did anyone else have that question? Raise your hand
I
if
had
you were
that
also wondering.
question.
Yeah,
I was
okay.
thinking the exact thing. I was going to go with it, but I was thinking the exact thing.
Okay, exactly. So we've learned a valuable lesson here, which is if you have a question, somebody else also has that question. So you should always, always ask questions. So there are no stupid questions. That's number one. Number two, the reason is I'm doing this because we're learning a new concept today, the concept of precision and recall. And when you first encounter those concepts, it's easier to do it thinking in terms of binary. So it's not necessarily like you have to do it this way. It's simply that because we're going to be looking at confusion matrices and precision and recall, it's going to be easier to absorb those ideas in the context of a binary classification problem.
So does that mean they would only apply for binary classification problems, or would they apply for non-binary as well?
The metrics that we're learning today apply to any classification problem. They just get a little funky looking once you get above binary. So we're going to start with binary and then move up. Always, always ask questions, guys. If you have a question, I guarantee you someone else has it. Okay, Beautiful. Thank you so much. Awesome. Great question. So, any other questions? Okay. So, let's do our two splits here. We have our target vector and our feature matrix. So we have our feature matrix big X and our target vector little y. And then we're also going to do our train validation split. So I know we talked yesterday about doing cross-validation and you no longer need a validation set. In this case, we're going to need a validation set to do a little bit of checking these metrics. So this is why I'm using a validation set in this case. All right, there we go. And then we'll establish our baseline. And by now, you guys know what the baseline is on this model. It's 54%. And then what we're going to do is we're going to use our model here. We have a random forest classifier. I'm going to reduce the number of estimators here to 25 just to keep things quick, but no other reason than that. And then notice that I've set number of jobs to -1 to also speed things up, and I have a random state here. So I'm going to hit Shift and Enter, and this will run. And then one thing that I want to do before we go on break is I want to just look at the feature importances for the model that we've created. So I'm kind of skipping ahead to the communication phase here, but I think there's something important we need to look at. So we've seen code like this before, so I'm not going to go over it in detail. I just want to plot this out and see what we have. And what we see here is that we have this column called status group. And it seems to be way more important than anything else in our model. So I'm going to set our timer for 5 minutes. And when we come back, or what I want you all to, hold on, I'm going to stop the timer. Okay. And when over the break, I kind of want to I want everyone to meditate. Why is it that status group is so important in our model? This feature status group, where does it come from? Why is this happening? And then we come back, we will discuss exactly what's happening. All right. So when we come back, I want to hear all your all's ideas. So see you in 5 minutes. All right, come on back, guys. Okay. So before the break, we had built this model, we had created a new target, and we had looked at the feature importances for our new model once we trained it. And we can see here that status group accounts for almost 90% of our decision tree here, of our random forest model in this case. It seems to be the most important feature by a long shot. So what's going on? What are some theories that people have? I see one from Eric. What do other folks think? Ven as well. And what Eric is saying is, Eric says that since our target was based off of status group, since it was our old target and we built our new target using status group, it is highly correlated. It is the exact same information practically as our new target. And so our decision tree or our random forest, is smart enough to say, oh, there are all these features that are like, they kind of help a little bit, but let's be honest, the most important thing is that old target. This one column seems to have all the information I need in order to predict whether a pump needs repair or not. So Kaji is saying, is it our Y hat? And in a lot of ways it is. It's like the only thing that our model needs in order to make its Y hat predictions. So whenever you create a new feature and you create that new feature using your target, you're going to have something called leakage. And the idea of leakage is when there is a feature in your data set that basically gives the answers. When you have a feature in your feature matrix that basically gives the answers about what's in the target vector to your model. It's basically kind of like telling it the future in a lot of ways. So for example, if I were thinking about our New York City real estate data set, if I had my target being the price of the property, and what I did was I created a feature called price per square foot, using that, the sale price, that would be something where that would absolutely be a case of leakage. Another way to think about leakage is my model, when I deploy it, when there is no longer a target and my model needs to guess, will that information be available to my model? Is my model going to know which status group? If I just say, hey, tell me about this pump, is my model going to know the status group? No, it's going to need to predict the status group. Or for example, if I'm building a predictor to see whether, let's say I'm a football coach and I want to build a predictor to see whether my football team, I don't know a lot about sports, guys, so this is a little touch and go here. But let's say if I want a predictor to see whether my my offensive team is going to score when they're inside the 20-yard line, so like yes or no, well, I can use lots of features, but one feature I can't use to train my model is number of yards gained during the play. Because one, that would be obvious, right? If it's like above a certain number, you win, right? You get in the end zone. But also, when I actually deploy my model, it's not going to have information to yards gained because I'm going to use that model to predict what's going to happen before the ball is snapped. Right? So think about when your model is going to be used and what information is going to be available to your model at the moment you're going to ask it to make a prediction. And if there's stuff that you're using to train your model that your model is not going to have access to when it's actually making its prediction, that's an example of leakage. And so whenever you see something like this, maybe you have one coefficient that's like way off, or like here with feature importances, it seems to be the only important feature. That's a good indication to you. That's a clue that you might have a leakage problem. Sometimes it's not a leakage problem, right? Sometimes it's just there's one feature and that's the most important one. But this is a flag for you to investigate what's going on. So in this case, what we'll do is if we go back to our wrangle function, and then what we do is we also do df drop, and we'll drop our status group. Make sure we do in place equals true. There we go. And then I'll just redo everything here. So I'll re-split my data. My baseline will stay the same. And then I'll retrain my model. And then finally, I look at my new feature importances. What we'll see is, these are the feature importances that we are familiar with, right? Latitude, longitude, quantity, GPS height. Everything seems like there's a good, all of these features are contributing in some way. This tells me like, okay, I think we're back on sound footing. So beware of leakage, because sometimes there's leakage in your data sets and you never know. Someday in your future, your near future, you might encounter leakage in a data set. As soon as tomorrow you might. So just keep that idea in mind. Any questions about leakage? Or about anything that we've seen so far? All right, let's move on here. So let's just check our metrics. Let's start with accuracy, our dear friend accuracy. And what we'll see here is what we've seen with most of our models, like with our random forest models. It does very well with the training accuracy, and the validation accuracy isn't quite as good, because we have that little kind of overfitting, but nothing grave, nothing terrible. And we're up at 81%, which is pretty good for this data set, even binary. But again, we know whether our model is getting things. Accuracy tells us what percentage of your observations are you getting right? What percentage are you getting wrong? In this case, we're getting 81% right, and then we're getting, 19% wrong, more or less. But that really doesn't give us a lot of information. It's like, yes, no, you got it right or wrong. But there's a lot more subtlety in this problem, which I think is worth exploring. And that's where these other metrics come in. So for example, the first kind of, it's not exactly a metric, but it is a way of understanding how or where your model is getting right and where your model is getting wrong, is called a confusion matrix. And so I'm going to put together a confusion matrix first. Let's do the coding first, and then we'll unpack what it is and what it's telling us. So up above, I imported my plot confusion matrix, and inside I'm going to put a couple things. The first thing that I'm going to put is the name of my model, which in this case is just model. The next thing that I'm going to do is I'm going to put in my validation data, and always be sure to use your validation data here. So that's why I did a validation split. So I have my validation here. So I'll do X val and Y val. And that's all I need right now. Let's run this and just see what we get. Oh, I'll put a little semicolon here to suppress the text output. And this is sort of helpful, but I feel like we could clean it up a little bit. Let's do a couple things. The first thing that I'm going to do is we have these ones and zeros here. And I guess we know that 0 means no repair is needed and 1 repair is needed. But it sure would be a lot easier if we actually had it written out. Because one thing when you're doing binary classification, you can get confused real quick. So we should probably put in some labels here. So we'll start with no repair needed. So no repair needed, that's our negative class. And then our positive class is needs repair. There we go. Let's try that. Whoops, I have an error here. Let's see here. Oh, I'm sorry, this should be display labels. There we go. Okay, that's looking better. The second thing that I'm going to do is we have these scientific notation, and I feel like this is not very easy to read. So let's change this. Let's change the formatting of this. So I'm going to go to values format, and I'm going to just round these. So I'm just saying like round them to no decimal places. And let's see what that looks like. Oops, I got another error here, syntax error. And that's because I'm missing a comma here. So I'll hit Shift and Enter. Beautiful. Now this is something that I can understand a little bit. Let me just take a version of this and drop it in the Slack so that you guys have it. There we go. And so here we are. And what's happening? Well, here's a good way to begin interpreting this. I'm going to, let's start with let's start with the yellow and the green here. So in our yellow column, or in our yellow box, what we have is these are the number of observations in our validation set where we predicted. So these are this is the prediction here along the bottom. We predicted that they didn't need repair, and comparing that to the true label, we were correct. So these were observations that we said didn't need repair, and they actually didn't need repair. So one way to think about these is we could call them, let's actually make an equivalent here. Let's make another box here. So we can call these our true negatives. So we said they were negative and we were right. The second one, let's look at the green box. Here, 4171, these are the observations that we said did need repair. So we predicted 1 and we were correct. They did need repair. So they're also true, but they are true positives. So they belong, we predicted they were in our positive class and we were correct. Our predictions were true. So we have our true positives and our true negatives. So along that diagonal, that's where we were correct. Now, along the other diagonal is where we messed up. So, for example, here, these were observations where we said they needed repair and we were wrong. So our predictions were incorrect we said they were positive and they were not. So those would be called false positives. And then the final one here is where we predicted that they did not need repair, but they actually did. So the $1 million question, what are these called? Well, these are also false, but in this case, they're false negatives, false negatives. So now I know what I got right and what I got wrong, but I know exactly how I got it right and exactly how I got it wrong. So here's a question for you guys. Where is our model screwing up the most based on this confusion matrix? Where is our model really dropping the ball? What do you guys think? Hector's saying false negatives. You're absolutely right. Tiana, you're absolutely right. Lots of false negatives here. So our model is not doing well when there are a bunch of pumps that need repair and we're saying that they don't need repair. Okay, that's good to know. Important information. So this is one area where you might say, oh, I see my model has a lot of problem with false negatives or false positives. That might give you some insight into the data. It might give you insight into something that's happening in your model. Now, any questions about this confusion matrix? Because I know that sometimes confusion matrix can be confusing. Curtis is saying it's also important to keep in mind that there is a kind of imbalance here. In this case, there isn't, well, in status group, you're right, CT, right? Here you're saying there's because we have basically in status group, half of our data is functional, half of our observations are functional, a quarter are, and then the rest are split up between functional needs repair and needs repair, right? But we're working with binary classification. So now it's about half do need repair and about half do need repair. So in that sense, it's balanced because we went to the new target. Other questions? Okay, so with this in mind, let's start thinking about a couple other metrics here. And I want to talk specifically about precision and recall. So let me pull up a good, let's talk about recall kind of narratively, and then let's also talk about it with a graphic as well. But basically, recall score is going to be another metric. All right, it's another score. So it goes between 0 and 1. 0 is bad, 1 is good. And you get some sort of floating point number between those two. And in this case, what recall score represents is it says of the pumps that actually needed repair, of all the pumps that needed repair. So everything in kind of this row, of those pumps that actually needed repair, what proportion of those did we correctly predict as needing repair? So of all of these that needed repair, how many did we predict actually needed repair? Another way to think about this, I love this graphic, I do it every time. It comes from our good friends at Wikipedia. Let's see here, precision. Oh, there we go, precision and recall. Let's look at this in a window. There we go. Okay. So here's another way to think of true positives and false positives. But the idea of precision is if we look at all of our true positives and our false positives, all right, and we compare that to how many that we got correct. So let's look at this. Let's actually calculate this by hand first. So if I want to calculate this by hand, I want to say that, okay, of all of those pumps that actually needed repair, so everything in this row, how many or what proportion did we correctly predict as needing repair? Well, the first thing that we need to do to get kind of the bottom part of that equation is we need to do, let's see here, we need to do 1, 2, 3, 3 plus, let's see here, 4, 1, 7, 1. So these are all the pumps that needed repair. And of those pumps, how many did we correctly predict as needing to be repaired? And so for us, that was 4, 1, 4, let's see here, 4, 1, 7, 1. Beautiful. And so what we can see here is that our recall for our model is 77% or 0.77. So that's what recall is about. Now let's talk about precision. And by the way, it's important to kind of have an idea about how to calculate precision and recall by hand, like we've done here, just to get a little bit of an intuition about how this confusion matrix works. And you never know, sometime in your near future, perhaps as soon as tomorrow, you may need to do this. So keep this all in mind. And now for precision, precision is a little bit different. So for precision, let me actually move this. Let me move this up here, just so it's right where we need it to be. There we go. So of all the pumps that we predicted as needing repair, so all the pumps that we predicted as needing repair, so this, what proportion actually needed repair? What proportion actually needed repair? So in order to get that first part, we're going to start again with 4171, and we'll add it to 929. We'll wrap it up. So that'll give us our denominator. And then for the second part, we would just put on the top of that equation 4171. And that would give us 81 or 0.81 or 81, whatever, however you want to say it. And so we can see that our model has better precision than it does recall. And that's precisely the reason, or the reason for that is that this number is big. So that's why our recall score is not as good as this smaller number, which is where we're getting our precision score. Now, I have a question for you guys. In any classification model you have, there's often a trade-off between, you don't usually get perfect precision and perfect recall. Usually as one goes up, the other one goes down. And so the question for you guys is, what's more important for a model that's predicting whether a water pump needs repair? Is it important to have good precision, or is it important to have good recall? So if you're repairing water pumps in Tanzania, or if you're predicting which water pumps need repair, is it more important to have good precision or good recall? And tell me what your thinking is here. Tell me where your answer is coming from. So Kaji's saying recall. Why do you say recall, Kaji? So Logan is saying, so like taking what Kaji and Logan are saying and putting them together here, if you have, right, real call, excuse me, recall is our ability to, let's say, let's use Pokemon here. Recall, gotta catch them all, right? Recall is our ability to identify all of the water pumps that need repair. Even if that means sometimes sometimes sending someone out to repair a water pump when it doesn't need to be repaired. So recall, gotta catch them all is very important if you want to make sure that everybody has access to potable water. Recall, gotta catch them all. You want to make sure everyone has a water pump that works. So recall is really important. So remember, recall, gotta catch them all. However, there's another way to think about this. What if I only had a limited amount of resources? What if I only had enough funds to conduct, 2,000 inspections? Well, if I had high recall, that means I would probably send people out to repair water pumps when they didn't need to be repaired. And so I would be wasting funds. Maybe in that case, if I had a limited number of, repairmen I could send out or funds that I could spend, maybe I would want to have highly precise model. That is to say, let's think about precision. Precision is about being really, really, really sure that a water pump needs repair. So only saying that a water pump needs repair if you're very, very, very sure it is. Recall is all about thinking, well, I'm not 100% certain, but it's better safe than sorry. Another way to think about it, and we'll talk about this and then we'll go to break. Let me pull up my whiteboard here. We'll do the whiteboard dance. Okay. Remember when now we don't have a logistic regressor here, but it would be helpful to think about a logistic regressor in this case. So here we have our 1 that needs repair. Here we have our 0, no repair needed. And let's say we're looking at, I don't know, longitude perhaps. I have no idea. And maybe we have a bunch of pumps where at a certain longitude, they don't need repair. And maybe after you get another longitude, like in the west of the country or the east of the country or whatever it is, there's more repairs needed. And from there, you do your little function and you get a little S-curve like this. And what we talked about previously is the idea of setting a threshold, where if my model gives me above 0.5 in that activation function, I would say, okay, repair it. And if I get below 0.5, I would say, no, it doesn't need repair. Well, one thing that I can do is this threshold doesn't need to be set at 0.5. I could raise it to 0.8 or 0.9, or I could lower it to 0.1 or 0.05. Now here's a question. If I lower this, that is to say, I make it kind of easier for me to predict that a water pump needs repair, am I favoring recall, gotta catch them all? Or am I favoring precision? So if I lower my threshold, what am I doing? So Curtis, Logan, Tiana, Angelo, you guys are killing it today. You're right. If I lower this, I'm favoring recall. And if I raise it, what I'm doing is I'm favoring precision. What I'm saying is I need to be really, really, really sure if I'm going to do this. If I'm going to do this, I want to be really, really, really sure. So again, the idea is, you as a data scientist are going to have some control over your classification model. And you can, in some models, favor recall, and you can, in other models, favor precision. And what you do will depend on the nature of the problem that you're trying to solve, right? Accuracy, again, is only half the story. You're going to need to think about what's more important in my model. Is it precision or is it recall? Any questions? Questions about what we've seen here with precision and recall? Okay, let's take another 5-minute break. And when we come back, let's think about how this precision and recall conversation, we can kind of put it into practice with our model here today. And Hector, I'll get to your question after break, okay? Thank you. All right, guys, come on back. Okay, let's do attendance. So here's what I would like to do. Let me give you all the codes. So the code for today is 9968. 9968. 9968. There we go. 9968. All right. Beautiful. Now that that's out of the way, let's go back to where we were. And one thing that I want to do before we look at our case study is I want to just show you one other clue. You know, you don't need to calculate precision and recall by hand every time. Scikit-learn has taken care of this for you. There is a precision score and a recall score, which we're not going to use. You can import them from the metrics module. But the one that I do want to show you is the classification report. So for the classification report, it's going to be the same way that we do all of the other metrics here. You would start with your labels, your true labels. So in this case, yval. And again, always use your validation data. Here we go. So I'll put in that. And then I want to compare that against my prediction. So this is the y hat. So I'll do model.predict. There we go. And I'll do predict xval. And then the last thing that I'm going to do is I'm going to use those target names again, because it's always better to label these things because you can get really confused real quick when it comes to what's 0 and what's 1. So the third argument that I encourage you guys to include is using target names. Target names. There we go. Beautiful. And another thing which I would do is if you just do this by itself, it's going to look funky. Just kind of, it's one of those things. So I encourage you to put it inside of a print statement. So we have a print statement, and I'll run this again. And now I can see my precision and my recall. Now, one thing to keep in mind here, notice how I have 2 rows. And so what's going to happen here is it's going to calculate precision and recall, basically saying, okay, let's say no repairs needed is your positive class. Let's say needs repaired is your positive class. And so just it's very important to remember that here, our positive class we're saying for this problem is the needs repair. So needs repair equals 1. Needs repair equals 1. So there's our precision, 82%, and our recall, 77. And then there's this thing called F1 score. F1 score is basically like a way to combine precision and recall into one score. It still goes between 0 and 1. It's technically the harmonic mean, but basically it combines those two. I like to just do precision and recall. I feel like you get much more information that way. And then we also have accuracy as well. So we can see precision, recall, and accuracy. And for me, when you're doing a classification problem, those are the 3 that you should really always look at: precision, recall, and accuracy. Okie dokie. So for the case study, I want to return to that idea about how are we going to deploy this, thinking about how we're deploying this model, why we're deploying it, what are our priorities. And by the way, Hector had a good idea of like, shouldn't it be important to also think about population when you're doing pump repair? That's a really good example, Hector, of thinking about like a data scientist doesn't work on an island. You're going to work with a team of people. And so thinking about those sorts of things, doing that kind of brainstorming, and then using your data science tools to like bring to bear on that problem are really, really important. So this is like a really, I like that kind of outside the box thinking. So here we are, we've got number of inspections. Let's say that the Tanzanian government, it costs $100 to inspect a water pump, and there's only funding for 2,000 pump inspections. So we're working here within certain constraints, budgetary constraints, resource constraints, I guess is what I would say. So let's think of 3 different scenarios here. Let's start with the first scenario, which is, let's just say that the Tanzanian government randomly chooses water pumps. They just pull water pump locations out of a hat that's big enough to fit 40,000 little pieces of paper in it, and they send someone out. And if it's repaired, great. If it doesn't work, not a problem. Or it is a problem, right? We waste those funds. So if I just randomly send someone out to repair a pump, how often will they encounter a pump that actually needs repair? Let's keep in mind here. Let's look at Y val. Let's do our validation data, and let's look at value counts, and let's normalize. There we go. So if I just randomly choose water pumps, how often would I encounter a water pump that needed repair? And remember that our column is needs repair. Yes, that's what I was getting to, CT, right? It's 45% of the time. So 45% of the time you would be correct. So you know what we could do is let's take the min of this. So there's that 45, and let's call that repair probability. All right, so we have our repair probability. So with that in mind, let's think about a couple things. One, I'm going to do a little bit of copy pasting code here, just because I want to make sure we get to everything. So if we do this, we're going to, whoops, I need to run the cell above. That's why I got a name error. There we go. So I've got number of inspections conducted, 2,000. And the number of pumps that I'm going to repair. So let's see here. This would be, let's say pumps repaired. That's going to be the number of inspections times that probability. So times that 0.45. So the number of inspections I do plus repair probability, that's 909. Let's round this number. Or actually, let's just make it an int. That'll be better. Okay, so I'll conduct 2,000 inspections. I will repair 909. And then the question then is, how can I calculate the funds that I've wasted? The funds that I've wasted. That's right, there you go. So it would be number of inspections. Number of inspections, that's right. And I would subtract the number of correct ones that I did. So I guess it would be something like this. Here we go. There we go. So those would be the number of inspections that I did. And then I would need to, actually, let me take this int out of here. This is getting a little crazy. There we go. Okie dokie, let's put this here. There we go. So this would be, how's the, what's a good way to do it? Let's, yeah, this is a good way to do it. Let's just do it this way. Okay, so I'll do number of inspections. There we go. And I'll put this here. I got to think about order of operations for a second here. So it would be like this. And then I would multiply that by 100. Is that right? There we go. Beautiful. And then let's put this as an int as well. There we go. Excellent. So I would conduct 2,000 pump inspections. I would repair 909 pumps, and I would waste over $100,000. Okay, so that's sort of our baseline here, is a kind of a way to think about it. The second scenario is, what if we just used our model out of the box? So we didn't worry about our threshold. We just said, okay, let's just say whatever our model does, let's do it. So we need to then think about what the best way is to calculate this. And the first thing that we should do is we need to be thinking about our validation data. Let's keep in mind what our validation data is. Oh, whoops, I have a key error here. Hold on. I should just use .head. I was thinking it was an array, but it's actually a series. So that's our validation data. And we would need to compare that against our predictions. So one way to do that is we could, let's just create a data frame here. So I'll do a data frame. And inside that data frame, I'll use that dictionary trick that we learned yesterday. So I'll do yval equals yval, and then my prediction, so y predict or y hat is going to be model dot predict xval. And then I'll put that into a data frame. So I'll just call this maybe results equals PD data frame, and I'll put in the data. Okay, beautiful. And if I look at results, I'll see that these are my true values versus my predicted values. Okay, now I can only do, let's say, let's think about this. So the first thing that I would do is I would need to limit these results to only water pumps that I predicted, that my model predicted as being a 1. So I would have to put together a mask, and I would do, for example, results, and I would say, give me the results where y predict equals 1. And from there, I would do, let's see here, results, mask. And that would give me, again, only things that I had predicted as being needing repair. Sometimes I'm right, like in the case of this observation. Sometimes I'm wrong, as is in the case of this observation. But let's say I can only do 1,000, or I'm sorry, only 2,000. So one way to do that is I can take a random sample. So let's just say I'll randomly sample 2,000 pumps where my model says that a repair is needed. So I can do number of inspections here. And if I look at sample.head, or if I look at sample.shape, I guess, these would be my 2,000 water pumps that I would send someone out to repair. And again, if we look at the head, I would say, okay, sometimes I get it right, sometimes I get it wrong. Let's see what happens. In fact, let's see if I look at the first 10. For example, in 10 of these, I'm getting it right, but it looks like in 9 of them, I'm getting it right, but in this one, I'm getting it wrong. So with that in mind, then let's think about number of inspections. So again, we'll print out our number of inspections being 2,000. And then we need to think about number of pumps repaired. And that's going to be, let's see here, that'll be my sample and my y-val. And actually, I can just sum it up. So I can say of the true values, or excuse me, I can just sum up the y-val column and say how many of those are 1. So I'll conduct 2,000 inspections. I'll repair 1,600 water pumps. And then for funds wasted, it would be, let's see here, number of inspections minus that number, that 1,643, which we would then need to multiply by 100. There we go. That looks right. Let's see here, there we go. And so what I can see is that my model right out of the box, I repair way more pumps and I waste way less funds, or way fewer funds, I should say. Okay, so we have this randomly isn't great. Our model out of the box is better, but what if we emphasize precision in our model? And let's say we only select pumps that our model is very certain need repair. So the first question we need to answer is, how can we change the threshold for our model? How can I not just get a yes or no? Thank you, Logan, for the lemon head, or the, what is it, lemon grab? Excellent Adventure Time reference. And Logan is saying, well, maybe you can look at predict probability. And let's remember, guys, that we looked at this in the module project earlier. Was it this week? I think it was this week, or it was last week, maybe. When we did, I could look at my model. I can do model.predict xval, and that will give me, yes or no answers, zeros or ones. But I can also do predict proba, which gives me the kind of degree of certainty. And in this case, I'm interested in that second column. So this first column, that's our 0 column, doesn't need repair. And then this second column is the column we're interested in. So I could just take all of the rows and just that last column. There we go. All right, so let's think about how this works. Again, I want to have, let's actually take this code and let's kind of play it around a little bit. Let's move it around a little bit. Whoops. There we go. So instead of y predict, let's do y predict proba. And we'll use this little bit of code we just created and drop it in here. There we go. So now if we look at results.head, we have the true label, and then we have our kind of degree of certainty that our model thinks it's a 1. And then from there, we can set our threshold. Let's set it at what do we say, 0.85? And then we can take our mask here, the mask that we did before, but we'll need to change it a little bit. So instead of masking results on y predict, we're going to do it on y predict probability. And instead of looking for something that is 1, we're going to look for anything that is bigger than our threshold. And so now if we look at our sample, these are going to be 2,000 pumps that our model is pretty certain need to be repaired. And you can see the first one were right, the second 2 were wrong, and so on and so forth. So what I can then do is I can just take this here and paste it in down below, and we can do the same thing. And what we'll see is if we increase our precision or we raise our threshold, we do 2,000 repairs, or we do 2,000 inspections, we repair 1,895 pumps, and the amount of funds we waste goes from 37,000 down to 10,000. And in fact, we can maybe even raise this a little bit without throwing an error. Let's see if we can get 2,000. Yep, there we go. I can even raise it a little bit higher, and it looks like we're okay. So in short, when you're randomly choosing, not surprisingly, you don't do so great. When you're using your model out of the box, which is just predicting yes or no, you do better. However, if what you're interested in is making sure you use your funds, your resources efficiently, you can raise precision, and that will increase the number of pumps that you repair within the limited number that you have funds to repair, and you also waste less funds. Andrew's asking, why is it that when we raise the threshold, the funds are wasted? It should have dropped. Well, I think the issue here is that, remember, we're doing a sample. So this sample, if we run this cell over and over again, you'll see that every time it's going to be a little bit different because the sample is going to be a little bit different. So it's just kind of natural variation if I'm just randomly choosing 2,000 pumps. This is, by the way, a good reason to set a random seed or a random state so that it works consistently. But we're being lazy today. Okay. Any questions? Questions about what we've seen? All right, let's do a quick review, and then we'll talk about what is on tap for today's module project. So we added one little line or two to our wrangle function where we took our multi-class classification problem and turned it into a binary classification problem. And we needed to be very sure that we dropped our old target because otherwise we would have leakage in our model. From there, we did our splitting of the data and establishing our baseline and then building our model. We used a random forest classifier. We used this feature importance to get a little insight into whether we had leakage or not. And then finally, we looked at metrics. And we looked at kind of the big three metrics when it comes to classification problems. We looked at accuracy, which really only tells you half the problem. We then looked at a confusion matrix, which gives you a little bit more subtlety as to what you're getting right and what you're getting wrong. We talked about true positives, true negatives, false positive, false negatives. And then we talked about precision and recall. So the idea of recall, gotta catch them all, getting all of the observations that are in your positive class. And then we also talked about precision, being very, very sure that something belongs to your positive class before you say, you predict that it is. And we talked about how there is a trade-off in models between those two. If you lower that threshold, you're favoring recall. If you raise it, you're favoring precision. And we even looked at a way to kind of do this all with a little one-liner of code, classification report. And then finally, we talked about our case study. So we talked about choosing randomly versus using your model kind of out of the box, and how you, as a data scientist, you can use predict probability to raise or lower that threshold depending on what is most important to you and how that model is going to be used. For today's module project, the last module project of Sprint 2, the big thing is, if you haven't submitted to the Kaggle competition, now is the time to do it. The other thing that you need to do today is submit your data set for the Build Week project. Beyond that, I want you to plot a confusion matrix for the Tanzanian water pump model. You don't need to make it into a binary classification problem, but notice how it's going to change the way the confusion matrix looks. It's going to be a little bit more confusing. And basically that's it. Look at the precision and recall of your model as well. Use that classification report. And that's it. Get that competition in and then work on your data set. The last thing that I want to share with you guys, it's 11. I promise we'll be out of here by the time we won't even get to 11:01, is I'm going to drop in Slack in the main channel. I'm going to drop, let's see here, 1, 2, 3, 4, 11 questions. So these are the 11 questions that you should ask yourself when you're preparing for the sprint challenge tomorrow, or that becomes available at midnight. So look through these 11 questions. If you answer yes to that question, you're in good shape. If there's a question where you're like, I'm not sure, or maybe not, that's a good opportunity or a good signal that you should talk with Cece, who's doing Q&A today at 2:30, or Isaac, who's going to be doing support hours at 5, or you can even check in with Isaac at 8 tomorrow, 6 tomorrow. All right, everyone? So that is all. As always, please do fill out that critical incident questionnaire once we are done. And that's everything from me. I'm a little late. Sorry, guys. I'll give you 2 minutes back next week. Actually, Cece is going to be teaching next week. So she's going to give you 2 minutes back. Cece, are we doing 60-minute models tomorrow?
Yes, at 2:30.
All right, excellent. So there's all sorts of fun things coming up in the calendar for tomorrow. And we'll be available at 8 o'clock, starting at 8 o'clock to answer any of your questions. And that's it. You guys have done a ton of hard work this week, and we're really, really looking forward to seeing you all kick the butt of that sprint challenge tomorrow. All right, so everyone stay safe, take care of each other. Happy data science. Bye-bye.